So continuing on with product rule, I have this first example. So I have an x cubed, which is a thing to an exponent, so I can use power rule on that. I have a radical x, which I could write as x to the 1/2, so I will be able to use power rule on that. But I have the small complication that it is not x cubed plus root x, it's x cubed multiplied by root x. So the distributive property of the differential operator doesn't help me in this situation. There's no plus here, there's no subtract here. So I can't just throw the operator onto each part individually. What I'm going to have to use is a thing called the product rule. And I'm just going to do it so that you can see how it works. And then we're going to do it again so you can see how it works. And then I'm going to formalize it as an equation and then try and convince you that it's working. So first thing you need to be able to do is to find the place where those two functions are multiplying each other. So it splits it right about here. I have the thing before the line and I have the thing after the line, and they are two separate functions multiplying each other. This is a product of functions. So if you go to do the derivative of this thing, so I'm trying to get df by dx, you're going to set yourself up a little bit of scaffolding in order to do it. I'm going to build a square bracket and a round bracket plus a round bracket and a square bracket. Now this, of course, this is just the structure that I'm offering to you. It's not an actual mathematical requirement. It's not part of the rules. It's a nice way to set the thing up so you can see what you're doing. What I'm going to do with this little structure is I'm going to take this piece and put its derivative here. That's why it's a square bracket. I'm going to take this piece and put its derivative there. Then I'm going to put this original function here and this original function there. So I'm just going to do it, and then we'll talk about why. So the derivative of x cubed would be bring the exponent down, keep the x, drop it by 1. Then I'm going to leave this part alone. Do you notice I did the derivative of the first half and left the second half by itself? In the next term, I'm going to leave the first function alone, and then I'm going to take the derivative of this. This thing would be x to the 1/2. So I bring the exponent down, keep the x, and subtract 1 from the exponent. So there you go. I'm done. I used the product rule. So the way this thing works is you see two parts. You take the derivative of the first, leave the second alone. Add to it the first one left alone times the derivative of the second. If you can do that, like puzzle piece, then that's it. That's the end of this skill. Derivative of the first, derivative of the second. All right, now, how to convince you that this worked? I'm going to do a little cleanup here. Right? So this derivative is 3x squared, and this is x to the 1/2. X cubed, and this is 1/2 x to the minus 1/2. Okay, now by exponent laws, an x to an exponent times an x to an exponent, you add them, right? Like x cubed times x to the 4 is x to the 7. So this thing here, df by dx, is 3 to the x. Well, that's 2 and that's 1/2. So call that 2.5 plus 1/2. That's a 3. That's a negative 0.5. So 3 minus 0.5 would be 2.5. Well, that's encouraging. Those of you out there on the internet screaming at me for poor notation are going to say you can't put a decimal in an exponent. Well, I guess I can. I just did. But for purity's sake, we're going to remind ourselves that 2.5 is the same as 5 halves. 5 divided by 2 is 2.5. Fix that there. Fix this. Alright. And if I were to finish this off, df by dx would be, well, I have x to the 5 halves and x to the 5 halves. So I can collapse these, gathering like terms. 3 plus a half would be 3.5 x to the 5 halves. And again, I'm going to satisfy the the purists out there, 3.5 is the same as 7 divided by 2. Okay. So this product rule delivered me 7 halves of x to the power 5 halves. If I were to take this thing and I were to try and collapse it using the exponent notation, that thing there is x cubed x to the 1 half, which is the same as x to the 3.5, which is the same as x to the 7 divided by 2. So to take the derivative of this, you should write the exponent in front, keep the x, subtract 1. 7 halves minus 2 halves would be 5 halves, and that is exactly what we ended up with. So this works. As far as a proof of it goes, I believe there's one attached. You can follow the link at the bottom of the page. It is a little intense. So take a look at it. You'll never be required to reproduce it, but it might be instructive to take a look at how it works. For now, what I need you to be able to do is to recognize when you have a function multiplied by a function. And once you have that, be able to do the derivative of the first, leave the second alone. Leave the first alone, take the derivative of the second. And if you have the fraction skills, try and boil it down into a single thing. So I'm going to clean this off and try another one. Okay. Now that does not look like a function multiplied by a function. So I'm going to have to manipulate her a little bit. First off, if I have anything in a fraction, there's nothing stopping me from writing the numerator 4x squared minus 3x plus 10 multiplied by 1 over x. That's a perfectly valid replacement there. Now I'm going to look at this thing and I'm going to realize that that's x to the negative 1. So I have this piece, which is a parabola, multiplied by a rational expression, and I can draw my dividing line there into my first piece and my second piece. So when I go to take the derivative of that, then dg by dx is, build yourself some scaffolding. I'm going to need to take the derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. I know I'm going to have to do that before I get started, so I might as well build myself some structure. So the derivative of my first part, wow, that's gross. New marker, it's getting a bit carried away. Ew. Bring the exponent down. 2 times 4 would be 8. Reduce the exponent by 1. 1 times negative 3 is negative 3, x to the 0, so I don't need that. And the derivative of any constant is just gone. Now I'm going to leave this one alone. Then I'm going to leave the first one alone, 4x squared minus 3x plus 10. And then I need to take the derivative of this, so bring the minus 1 in front, keep the x, drop it by 1. I get that. All right. So if I clean that up a little bit, I have 8x minus 3, and this is over x. In this term, I have 4x squared minus 3x plus 10, and that is over x squared, and this negative times a positive is negative. Now, I have a fraction minus a fraction, and the denominators do not match, so I'm going to try and fix that. I can make these match if I put an extra factor of x in the bottom, which means I'll have to introduce one in the top. So if I do that, my next line in the derivative would be dg by dx is 8x squared minus 3x minus 4x squared minus 3x plus 10 all over x squared. Okay. 8x squared subtract 4x squared leaves me with 4x squared. Minus 3x's minus 3x's is gone. Minus 10 be negative 10 all over x squared. And if you like, you could separate that as two separate fractions. 4x squared over x squared minus 10 over x squared, which is the same as 4 minus 10 x to the negative 2. As these undo each other, leave only the 4 behind, and this was an x squared in the denominator. So how did that happen, you might ask? Well, I'm going to erase this much so that it's out of the way, and I'm just going to keep my answer here so we can compare. This function is the same as 4x squared over x minus 3x over x plus 10 over x. Now that's the same as an x squared divided by an x is just 4x. 3x divided by x is just negative 3, and 10 over x, well, that's 10x to the minus 1. So if I were to go and take its derivative, dg by dx is, well, keep the 4, bring the 1 in front, reduce the x by 1. This is a constant, so its derivative is gone. Derivative of this one would be keep the 10, bring the minus 1 in front, keep the x, drop the exponent by 1. So x to the nothing is just 4. This is with no value, negative 10x to the negative 2, which is exactly what I got the long way. So there are two lessons to be learned from this example. Number one, product rule works because you get the same answer using product rule as you do if you spot a way to reduce the function. Lesson number two, if you can spot a way to reduce the function before you get going, then you can skip the product rule entirely maybe. So work smart, not hard, right? You're trying to try and see if you can use your fraction skills and your radical skills in order to break these down into simpler things first to save yourself some work, whichever you like. Okay, but with this match, I've confirmed once again that if you have a product of two functions, you get its derivative by doing the change in the first, leave the second alone, plus leave the first alone, derivative of the second. One more example of this, I'm going to try a three-way one, and then we'll try and talk about why this is happening. Okay, I have x cubed times the square root of x times the x to the power 5 cube root. Okay, so first off, this would be x cubed, x to the 1/2, and then this thing is an x to the 5 that happens to be in a cube root, x to the 5/3. So exponent laws say I could do that as x to the 3 plus 1/2 plus 5/3. I can get this in a common denominator with sixths. So that's 18/6 plus 3/6 plus 10/6 is x to the 31, x to the 31 over 6. So when I'm done here, my derivative should be, so that was f. Therefore, df dx should be 31/6 of x to the 25 over 6. So I brought the exponent in front and reduced it by 6/6. Okay. Now, this is a three-parter. So to do three parts, you just need to have three terms, right? We're doing the derivative one piece at a time. So dk dx then is going to need a square bracket for the first part, and then you leave the other two alone. And then you're going to leave the first one alone and take the derivative of the second. And then you're going to run out of room. Leave room for the first one, for the second one, and then derivative of the third. Okay. So in they go. Derivative of x cubed is 3x squared. Leave this alone. Leave that alone. Leave x cubed alone. Derivative of 1/2 x, or x to the 1/2 would be 1/2 x to the negative 1/2. Leave this one alone. Then I leave this one alone. Leave this one alone. This would be, that's x to the 5/3, so 5/3 x to the 2/3. Done. Now that's an unholy mess, but hey, that's what we do here. So my derivative then, dk dx, would be 3. 3 is the only number. X squared x 1/2 x to 5/3. This be 1/2 is the only number I have. X cubed x to the negative 1/2 x to the 5/3. This, the only number I have, is 5/3 x cubed x to the 1/2 x to the 2/3. Okay, so how am I going to simplify this? Okay. dk by dx is 5/3 is the same as 1 plus 2 extra thirds. I'm going to borrow that 1 and tack it onto this. I'm going to do it again in this term, but instead of tacking it onto the first one, I'm going to tack it onto this. So 1 plus a negative 1/2 would be 1/2 x to the 2/3. Back here, I have 5/3 x cubed x to the 1/2 x to the 2/3. Notice that these match. I don't have to have them all combined in order to gather like terms. So I have a fraction here. I'm going to need to do some common denominator. Let me just write dx is 3 plus 1/2 plus 5/3 x cubed x to the 1/2 x to the 2/3. I'm going to change these numbers into sixths. So 3 is 18 divided by 6. 1/2 is 3 out of 6. 5/3 would be 10 out of 6. So that gives me a grand total of 18 plus 3 is 21 plus 10 is 31/6. That's encouraging. Now if I were to put these into 6, 3/6 is 18/6. This is 3/6. This is 4/6. (18 and 3 is 21. 21 and 4 is 25/6, which is what I had up there in the first place. So a three-way product rule it's not harder than a two-way product rule. It just has one more term. Because you're taking the derivative of each part separately, if it has 3 parts, it needs 3 terms. If I tacked a 4th piece on here, it would need 4 terms. If I put a 5th on, it would need 5 terms. It just expands outwards as you add more pieces. So hopefully you've got power rule under control as far as doing it. You can take a read through the algebraic proof if you like to see how this plays out that way. I'm going to try and erase this and try and give you a little bit of a physical justification for why this is working the way it does. Okay, so to try and break this down with no algebra, no math, allegedly, we're going to start out with a very simple example of how much you get paid every week. So the way your paycheck is calculated at a very basic level is you are paid a certain amount per hour and you worked a certain number of hours. So if you work 10 hours at $13 an hour, you were paid $130, right? This times this is this. So the value of your paycheck each week is the product of 2 functions. One is how much you're paid per hour, and the other is how many hours you worked. So I'm going to use the derivative notation here a little bit, but instead of writing d by dx, I'm going to write change over time, or just change in. Your paycheck. Okay, so if I want to change the amount of money I'm paid every week, there's 2 ways I could do it. The first thing I could do is change my hourly wage. I could get a raise, or I could have a salary cut. Hopefully it's a raise. So if I've changed my wage, change in wage, I would get my new salary by taking my new wage, the change in my wage, and I would multiply it by the hours I'm working. Okay. The other option is to leave my hourly wage alone so I'm paid the same rate, but I either increase or decrease the amount of hours I work. So that would be a change in the hours worked. And if I did both of those things, right? If I increased my wage, I would take the amount my wage went up, multiplied by the hours I was already working to find out how much that increased my check. And then I would take the base wage that I was already making and multiply it by the extra hours I was working, and I would take the pile of money there and the pile of money there, and I would add them together in order to get the increase in my normal paycheck. So if you look at what's happened there, the derivative of this, right? Derivative is a slope, and a slope is a rate, and a rate is a change in something. The change in this, the derivative of this, was the derivative of the first thing, leaving the second one alone, or leave the first one alone and take the derivative of the second one. So this is a very familiar idea and like very logical if you think about how it's set up without putting all the squiggles and math symbols in it. If you want to change something that's a product of two, the way you manifest that change is to either change the one or change the other. Okay, so in conclusion then, you should be able to take something that is a product of two functions, and you should be able to take the derivative of the first, leave the second alone, leave the first, take the derivative of the second. There's a bunch of questions in the practice problems like that, and then we'll get more practice with it as the course goes on once we introduce derivatives of sines and cosines, and of exponentials and of logarithms.